All right, we're finally at the end, the last content in this section called difference quotient. In order to help us understand difference quotients, we've got to do some side work. So I'm going to leave this worksheet for just a minute, and I'm actually going to come to this worksheet right here. We need to review function notation to help us understand difference quotients. So on this worksheet right here, I've got 4 different sets of problems. I have 1, 2, and at the bottom 3, 4. So we'll do a couple of these, and then the ones that we don't do, I will post the key with the answers so that if you need a little more practice, it'll be there for you. Alrighty, before we get to difference quotients, let's review notation. It says, given f of x or y equals 6x minus 9, find the following. Well, we're supposed to find f evaluated at x equals 2. Remember that what's between the parentheses is the x value, or the input that goes in for x in this equation. So what we're going to do is we're going to take f of x equals 6x minus 9. We're going to plug 2 in for this x, which we've already done here, and then we're going to plug 2 in for this x. So 6 times 2 minus 9. I'm going to write f of 2, the notation down here. This is 12 minus 9, which is 3. As a reminder, this is function notation, but that also implies that the ordered pair 2, 3 is on the graph of f. All right, so what's f of negative 3? So again, we return to the original equation. I plug in negative 3 here, I plug in negative 3 here. So 6 times negative 3 minus 9. Okay, down below, I'm going to use that space and clean it up. So right to the calculator, negative 18 minus 9 is negative 27. Okay, notice that right here I'm changing gears. So I don't have a number to evaluate in for x, but I have another letter. But it follows the same set of steps here. So wherever you see x in the original problem, here and here is where we're going to replace this input value of a. So f of a, this now turns to a, becomes 6 times a minus 9. Because a is not a numerical value, we can't clean that up, so we're finished. That is our answer. All right, what's f of h? Again, return to the original problem, plug in h here, plug in h here. So we get 6h minus 9. Okay, now let's look at what's happening next. Now look between the parentheses and we see a plus h. That means all of this becomes our input. So that's our new x. So we have f evaluated at a plus h. So right here where this x is, in front of the 6, we've got to plug in a plus h. And I'm going to put that in parentheses. Now don't forget the minus 9 because it is part of the original problem. So think of this as your x value here. So rewriting this notation, this function notation. Now what could we do here? Well, I guess I could distribute the 6 inside this parentheses because that is implied multiplication. So I'd end up with 6a plus 6 times h, or 6h, and then don't forget the minus 9. Okay, and here's really what we're trying to achieve to help us with what we're doing with difference quotients. So what's the function evaluated at x plus h? Again, x plus h gets replaced in here for this x, and then right here where this x is in the original problem, we'll put a parenthesis. Don't forget the minus 9. In the original problem, this was just x, but our new input, this is our input value, is x plus h. All right, well, this problem suggests that we're going to do the multiplication. So I'm going to bring down this notation. I'll distribute the 6 inside the parentheses. I'll get 6x plus 6h minus 9. There's no like terms here. It doesn't clean up, so that would be my final answer. So this is actually what we're going to need for difference quotients, is to know how to put an input value that's real weird and strange into an equation. Okay, let's go ahead and finish this problem right here, and I'll leave these other 2 for extra practice if you need them. All right, now given this function f of x equals, this is a quadratic equation. A reminder, this is a linear equation because this is a polynomial where the highest exponent is 1. So we evaluated this linear function for all these different input values. Now it's time to take a quadratic equation and evaluate it for all these input values. So notice they're all the same exact input values that I had in the previous problem. All right, what's f of 2? Well, 2 goes here for our new x, and 2 goes in for this x, And 2 will have to also go in for all x's, so this one as well, plus 1. So you'll go to the calculator, you'll perform all these computations, and you end up with an answer of 3. All right, let's try another one. What's the function up here now, this quadratic equation, evaluated when x is negative 3? So notice that my parentheses here that I have represent the x's that are here, but my new x, instead of this x, is now negative 3, here and here. We'll go to the calculator, we'll do all this work, and we end up with 28. We're changing gears. Our new input is a. So a goes here, here, and here. So we end up with 2a squared minus 3a plus 1. There's nothing to evaluate here, and there's nothing that collects. We don't have like terms, so we're finished. Okay. Likewise, our new input instead of x is now h. So h here and h here. Okay, here's where it gets a little more cumbersome because our input is another expression. So now we want to put a plus h in for all the x's in the original problem. So I'm going to write the original problem, but put parentheses where the x's are supposed to be. A plus h gets inserted here and here. Okay, this is kind of cumbersome, and a couple of our problems with difference quotients involves us generating this expression and then also simplifying it. All right, so let's take a look at what's going on here. In order for me to simplify this, I'm going to focus my attention on this first term here. Okay, following the order of operations, I've got to do the power first. I have to square this binomial, and then once I get that answer, multiply everything in that answer by 2. Then I'll come back and distribute this 3 and add the 1 and see if anything else kind of collects or cleans up. So I'm actually going to go off to the side somewhere, and I want to calculate this first. What is a plus h times itself? Well, this means we're going to have to FOIL. Okay, let's see if we can remember. A times a is a squared. A times h is ah. Then h times a, which can be rearranged to be a plus h because of the commutative property, and then h times h, which is h squared. These two terms will collect. We've got a squared plus, not only do we have one ah, but we have another, that coefficient in front could be a 1. We have one ah term group plus another one, so that makes us have 2 ah terms plus h squared. So all I've done so far is FOIL. So let me bring this notation down. It's going to get kind of crowded. I still have the 2, but now inside here, I'm going to put this trinomial, 3 terms, a squared plus 2ah plus h squared. Okay, so now I've completed this task of cleaning up this term. Now it's time to move on to this next term. Thank goodness. All I have to do here is distribute a negative 3 in. So negative 3 times a is minus 3a, and negative 3 times h is minus 3h. And don't forget the plus 1. Whew, there's a lot of algebra. Okay, next step. I'm gonna need some more room here. Okay, notice that we need to distribute this 2 inside this trinomial. So 2 times a squared is 2a squared. Plus, now this word gets a little bit tricky too, 2 times 2ah. Multiply the 2 2's and get 4 and keep the ah. So now I have double the double ah terms. Multiply 2 inside and get 2h squared. Okay, and now I'm right back here where I'm just going to just bring this back down and put minus 3a minus 3h plus 1. So let's take a long look at all of these terms and see if anything can be collected. Well, I don't see another a squared term. I don't see another ah term. I don't see another h squared term, nor do I see common terms with these last 3 terms here. So as a matter of fact, this is my final answer, as ugly as it is. This is what we're going to need for some of the problems upcoming in difference quotients. And I wanted to practice this skill outside of the difference quotient so that we kind of have an understanding of what we're doing when we go into that kind of involved problem. Okay, let's do one more. What is, if we can remember, what is f evaluated at x plus h? So my new input falls between these parentheses. This is my new x right here. So writing the original problem down, but everywhere I see x, put a big parenthesis so that I can insert now x plus h and x plus h. Do we have cleanup to do? We sure do. Just like in the previous problem, we have to follow the order of operations. So bring this notation down. Now let's focus our attention over here. We're going to have to FOIL this. So I'm going to have 2 in front, and once I FOIL, I'll have something to put in here. So following what we did here, but making the A's the H's, or excuse me, making the A's the X's, okay, and if I clean it up, this is what I'd get. So I just kind of went off to the side and did this FOIL, and then after I cleaned it up like I did here, I inserted it into this, this parenthesis. Okay, now I'm back here, so now I can distribute the -3 into this quantity, so minus 3x minus 3h, and then the plus 1 is just on its own. So let's take a look at what we have here. Am I done cleaning this up? Nope. So bring down the notation. Now we need to distribute the 2 in, like we did in the previous problem, so we get 2x squared plus 2 times 2 is 4, we keep the xh, and then don't forget the 2 times the h squared. I would recommend, putting these little arrows here because it helps remind you that you have to distribute 2 into all the terms that are within that parenthesis. And then I will just bring down the rest of the problem. I'll take one last look to see that nothing cleans up. So actually, this right here is our answer. Okay, I've provided 2 extra problems for extra practice, same idea here. So if you want to try these on your own, if you feel like you need more practice, and then consult the key to see how you did. So we're going to be using these skills here in a minute so that we can solve difference quotients. Okay, before we solve difference quotients though, to give you an understanding of what is, let me put this here. Okay, to help you also to understand what all this is right here, because there's a lot of letters going on right here. Okay, I'm going to connect to another example of finding slope, because that's basically what we're doing when we're finding difference quotient is we're finding slope. Okay, so let me set that aside. I'm going to go to some notebook paper, give you some more background so that when we get to the difference quotients, it all kind of comes together seamlessly, hopefully. All right. So what we want to look at first is slope of a line. And I'm going to put up here notes 2.2 because it's chapter 2, section 2 to remind myself. Okay, I'm just going to draw this random linear function, something like this. And what I'm going to do is I'm going to choose 2 ordered pairs on this linear function. I'm actually going to go over to x equals -2 and up to a height of 3. So the labeling on this ordered pair is -2, -2, +3. It looked like a -3 because that tick mark. Okay, and if I said -3, I beg your pardon. We're going to go left 2 and up 3, so -2, 3. Then I'm also going to choose maybe the point 4, -1. I'm going to call this point right here 4, -1. Okay, if I want to find the slope of this line, and I've got 2 ordered pairs or 2 points on this line, okay, I'm actually going to find a change in y coordinates over a change in x coordinates. And this little triangle symbol represents a change in. Sometimes it'll be read as delta y over delta x, but all that means is a change in the y coordinates of these 2 points divided by the change in the x. So we're trying to find the slope of this line. Sometimes you'll see that as m. That lowercase m represents the slope of a line. But to find the slope or the rate of change from this point to this point, we use a difference quotient. So this is a fraction bar, and it's going to represent a quotient. And that slope is found by taking the difference of two y coordinates, where this represents one of the y coordinates and this represents the other y coordinate, y subscript 2 minus y subscript 1, over a change in the x coordinates of 2 points on the graph. And again, these represent two different x's and two different y's. So for example, I could call this ordered pair x subscript 1 and y subscript 1. If this is my second point, I could call this the x coordinate x subscript 2 of my second point, comma, y subscript 2, the y coordinate of my second point. So how do we find the slope of this line? Well, it looks like it's going to be negative because my graph is decreasing. Well, now that I have some numbers, let's see if I can insert those numbers. So y2 is negative 1, the second y, minus y1, which is this first y coordinate, which is 3. So I subtracted these two y values. Okay, now in the denominator, I want to go to x subscript 2, go back to the first point I started with, and I'm going to take the difference of the two x coordinates, or 4 minus negative 2. So I'm going to work down here. So now we have a difference quotient. We're subtracting. We have a subtraction and a quotient. So negative 1 minus negative 3 is negative 4. And of course this would turn to adding 2. So we get 6. So I can simplify this to negative 2/3. There's a common factor of 2 that divides out of both those numbers. Makes sense that my slope, and if I bring this down, my slope is m. Okay, it makes sense, okay, that my slope should be negative because my line is decreasing. So I probably don't need one of these equal signs here, and I'm just going to connect that the change in y over the change in x, also known as m, is equal to negative 2/3. We're kind of far away, but that's okay. All right, so we just did a difference quotient with numbers on an easy problem, and we're kind of building to the more complicated ones. So to kind of get us started with understanding what's on our notes worksheet, I'm actually going to find the slope of a graph. Instead of a linear, well, I guess a linear function is also a graph, but I'm going to find the slope of a nonlinear graph. So I'm just making this up. Let me get a coordinate plane. Okay, and I'm going to get this random kind of graph right here. And I'm going to choose a couple of points on this graph. As a matter of fact, I'm going to choose, maybe if I can, the same 2 points that I chose over here on this line, meaning I might choose the ordered pair negative 2, 3. We'll just say this is negative 2, 3. And I might also choose, if this is 4, the scaling might not match up, but maybe I'll say this is 4, negative 1. So kind of in the same location. So when I say slope of a graph, I really mean what's the slope between 2 points that I've specifically chosen on this graph. So, and I specifically chose these 2 points. Well, if I connect these 2 points right here, the slope here should be the same as what I had here. The slope of this line should be same as the slope between these 2 points on a graph. So when we look at a graph and not a linear function and we choose 2 different points, I mean, similar to what we did here, we're actually finding the slope of a secant line to a graph. Slope of a secant line. That word secant indicates 2 points. And I'm going to put slope of a secant line of a graph. And I'll put a here. All right, well, we should expect the same answer that we got here, okay, because we're still going to be doing the same difference quotient. Change in y, change in x equals m, okay, equals, and we'll have the same exact values that we chose over here, so my answer should also be negative 2/3. So what we're going to be interested in today is finding the slope of a secant line of a graph that's nonlinear. We're going to have some kind of curve. We'll get 2 specific points. How do we find the slope between them? We use what we call this difference quotient. Remember, difference means subtraction. We've got it here on top and here in the bottom, numerator and denominator, and the quotient is when we actually divide them. All right, let's see if anything that we did here will help us make some connections to this this graph that we have over here that looks a little scary because it doesn't have numbers on it. All right, back to what we're supposed to be doing. Whew. The difference quotient is the slope of a secant line. What's a secant line? Well, it's a line through 2 points on a graph. Okay, what's the slope of a line? Well, it's represented by the lowercase letter m, and it's a difference quotient, the difference of the y-coordinates divided by the x-coordinates. What's the slope of a secant line? Well, this is kind of scary looking, but it's actually the same thing as what we have here. It's just when we don't know the actual ordered pairs, the numbers that represent the 2 points that we want to find the slope through, we have notation that represents that. Okay, so this is the formula that we're going to be using in our work today. Okay, so let's see if we can equate that with what's going on over here. Okay, here we have a coordinate plane. Here's our x-axis right here, and here's our y-axis. And we're kind of looking at just quadrant 1 right here. Okay, this was color-coded, but it didn't come up that way. But this is a portion of a graph that's nonlinear, and it's heading up this way. Okay, if I selected this point and this point as 2 points on this nonlinear function, and I connected through them, I just drew in a secant line, a line through 2 points on this graph. Okay, so let's label some points that are on this graph. Let's label this point. Well, from the origin, I would travel to the right. I don't know what this x value is. Maybe it's 4. I don't know. But all I know that I've moved over horizontally some distance x. And when I've traveled up and I intersect this curve, then how high is this graph? What's the y-coordinate? Well, I don't know what it is, but I know the notation f of x could represent how high this graph is. I could plug in x to the equation if I had it and get that y value. So right now, all I can do is use generic notation to label this ordered pair. So its input value is x, but its output value is comma f of x. It'd be like if we had 2 numbers here. All right, what's the notation up here that represents this second point that's on this graph? Well, notice that right here when we're at x, I want to slide over to the right some amount, I don't know how much, but I'm going to call that horizontal distance from here to this x-coordinate of the other point. I'm going to call this horizontal distance h. So what's the label of this point right here, this x-coordinate? Well, it's x increased by or added to by h. So that's my new input value. So let me come up here. So my x-coordinate is x increased by that h, comma. So what's the y-coordinate up here? Well, how do I get the y-coordinate? Well, if I knew what this number was, I would plug it into the function, and I would get f evaluated at x plus h. I would have to know what this x value is to get the y value exactly. So right now I'm just working with notation. So what is the slope between these 2 points as represented by this straight line here? Well, it's no different than subtracting the y's on top and dividing by the difference of the y's in the denominator. All right, so what are the 2 y values? Well, one of the y values is up here and the other y value is here. So when we write it across in the numerator, we've got f, some function, evaluated at x plus h minus this y value, f of x. All right, what goes in the denominator? The difference of the 2 x-coordinates. Well, what's x plus h? Always return to the same point we started with. What's x plus h minus x? Again, what's x plus h, this x, minus this x-coordinate. Notice that these x's cancel, leaving that the horizontal distance between these 2 x-coordinates, or the change, is actually just h. So a lot of background to help us understand what we're about to do here. I think we're ready. All right, so here's an example all worked out for us. Find the difference quotient on f of x equals 3x plus 5. So this graph right here has some name to it, some equation. I don't know what it is, but let's just say that maybe we're working with the function f of x equals 3x plus 5. How do we find the difference quotient? Well, we use this formula right here to help us find that answer. So notice that right here we start off with the formula. We put it right in front of us. Okay, well, what goes in the numerator for f of x plus h? Well, I don't know until I find it. So it's going to be my job to come over here and find f evaluated at x plus h. Well, based on that worksheet that we did, this is our original equation. If I replace that x with x plus h, that means where this x is in the equation, I'm going to put an x plus h in here, and then don't forget the plus 5. Okay, so what happened from the formula to here is that right here in the numerator, f of x plus h is going to be replaced with what we found f of x of h to be, which is this right here. So f of x plus h gets replaced with this quantity right here. They're the same. Okay, now minus f of x. Well, what's f of x? I need something here. Well, f of x is the original problem, 3x plus 5. So notice what we have up here in the numerator. We've got f of x plus h minus f of x. We're subtracting these two expressions. And then in our formula, we just always have just h. So I can't work with function notation and do algebraic things with it, so I've got to find replacements for each of these two things. One they're going to give me, and it always falls behind the subtraction sign, and that's the original problem. But my responsibility is to find out what f evaluated at x plus h is by doing what we did on that other worksheet and plugging in x plus h here and generating this equation right here, this expression that goes up front. Okay, so from this row, or from here down to here, okay, notice what they did. They distributed the 3 inside this parenthesis and got 3x plus h. Where'd the plus 5 come from? From right back up here. Now we're at the minus sign. Okay, notice that they distributed that negative, because this can be thought of as negative 1 through all the terms that were within this bracket. We could have used parentheses, but brackets is another grouping symbol. So distribute the negative 1 through, and you're going to get minus 3x minus 5. Okay, well, what happens next? Well, if we did everything right, things should cancel. These terms will cancel, the 5's will cancel, and we're actually just left with 3h over h. Algebraically, if we're dividing, we can divide out that common factor of h here, and our final answer is going to be 3. There's a lot going on there. Okay, so it's time for us to do an example. If we look at number 2, this is going to be pretty involved because we're not working with an original problem that's linear, where the highest exponent is 1, but where it's quadratic and there's a lot of algebra, just like that other worksheet where we saw that there was a lot of algebra. I will come back to this, but I want to do another easy one first. Okay, so I'm going to turn this worksheet over, and I'm just going to do an extra example. Okay, how are the directions going to be worded and how we're going to know what to do? The directions will be worded something to this effect. Find the difference quotient for f of x equals 6x plus 1. And you will be given this formula. Here's the difference quotient formula. We want to find the difference quotient when the function is 6x plus 1. Okay, I might suggest coming over here and generating what else you need. Meaning, right now, we have f of x, which is 6x plus 1. And we're going to insert 6x plus 1 in this position right here, but we need to generate f evaluated at x plus h. So what is f evaluated at x plus h? Well, based on that previous worksheet, we took x plus h and we replaced it in for that x, and we ended up with this expression. And then we distributed the 6, and I'll do that over here. So now it's time to enter 6 times quantity x plus h, this right here. This is equivalent to f of x plus h. So right here is where we're going to enter what's in orange. And right here, for f of x, we're going to enter what that's equal to, the function 6x plus 1. So we're subtracting these two y values. So I might suggest kind of working to the right a little bit. So build your fraction bar, make it pretty big, put an h here. What do I put in for f evaluated at x plus h? Well, I put in 6 times quantity x plus h plus 1. All I've entered is this quantity right here. Now minus, and now I have to enter 6x plus 1 because that's what f of x is equal to. But be careful, it needs to be in parentheses because you're going to have to distribute that negative through. I would always caution you that after the subtraction sign, whatever your f of x function is, put it in parentheses. Now I'm going to work down. Am I done? No, I've got some cleanup. Now I can perform algebraic moves on this numerator. So let's distribute the 6 in, 6x plus 6h. I've got this plus 1. Now I need to distribute this negative 1 in here, and I get minus 6x and minus 1. Denominator is just that little h. Take a look at this. Can things cancel? If we did our work right, they should. The 6x's cancel, the 1's cancel. I'm left with 6h over h. Because I'm dividing, I divide out common factors now, and my final answer is 6. If you're seeing a pattern that the answer is this coefficient on x with a linear function, you're right. That pattern applies to linear functions. Okay. All right. Now I want to go back to one that's a little more complicated, and we'll look at number 2. As a matter of fact, looking at the time here, what I think I'll do is I'll just stop, and I'm going to complete this in the next video with an additional example as well.